The field frame of a DC motor consists of main field windings, interpoles, and in some cases series field windings and even compensating windings. Series field windings and compensating windings are not included here. These windings are sometimes found in larger DC motors. Other windings located in the field frame are the interpole windings. Interpoles are identified here with red arrows and are designed to improve the motor's commutation and reduce the effects of armature reactance. Interpoles are also known as commutating poles. These poles are connected in series with the armature, therefore the wire size is large. Interpole windings are not wired in with the field windings. Even though they're mounted in the field frame, they are part of the armature electrical circuit and separate from the main field circuit. Now, the purpose of the interpole winding is to provide a more symmetrical and uniform magnetic flux field throughout the field frame. They counter the distortion in the main field flux caused by interaction between the armature and the main field. That interaction and distortion is called armature reactance. We will learn more about these important topics in later lessons. The interpoles are mounted in between each field pole. There are the same number of interpoles as there are field poles in a DC motor. In this picture, we see 2 of the 4 field poles and we see 1 of the 4 interpoles. And here we have a larger DC motor frame that includes 6 main field poles, 6 interpoles, and even has compensating windings. Compensating windings are the large bars inserted in the main field pole iron. In that previous slide, we saw compensating windings. These windings are installed in the field frame to help improve the overall performance of the motor. They're installed directly in front of the shunt poles. In fact, they're even inserted into the shunt pole iron. And like interpoles, these windings are designed to counter armature reactance. Compensation windings are wired into the armature circuit. They consist of large wire and copper bars. As the size of the DC motor increases and the current increases, interpoles alone may not be adequate to keep the field flux symmetrical. Also, sudden large armature current changes cause flux that negates the main field flux, and that can cause a sudden change in motor speed. So compensating windings are placed directly in front of the field pole, and they therefore counter the negating effect of high armature current and high armature current swings. Here's a closer look at the 2 poles with comp windings and 1 of the 4 interpoles mounted between the field poles. Here's a 6-pole field frame with shunt poles, interpoles, and compensating bars installed in the pole iron. This picture is not showing the pole face connector assembly, otherwise known as gain connectors, that connect the comp bars together. Here the pole face connector assembly is installed. This is style assembly. Each connector is made up of 2 thin bars, ceramic insulators, and bolting hardware. This bolting style has 2 thin bars that sandwich the pole face bar, and some users have a requirement for any DC that comes to the repair shop with a bolted gain or pole face connector assembly should be converted to a brazed connection. This process must be performed carefully. A concern will be that with their bolted style connector assembly, it takes more heat during brazing because there's 2 sides that have to be done. The heat is being transferred down the pole face bar and can compromise the pole face bar insulation, and that's actually been experienced. So when this is done, we have to be very careful of the processes that are used. Here's an example of a pole face connector assembly that's brazed. Some motors have series field installed in the field frame. In a compound motor, the series field winding is wrapped around the shunt pole winding. The series field is connected in the armature circuit, and therefore the wire size is large. These 2 windings must be insulated and completely isolated from one another. The series winding is connected to aid the shunt winding in our typical cumulative configurations, where the series field aids the shunt field. Some motors use the differential configuration where the series field is wired to subtract from the main field. That is not our typical motor. For compound and stabilized motors, it is critical that the windings are wired correctly, and we do not wire a cumulative motor as a differential connected motor. We will learn later about 3 DC motor types such as the shunt DC motor, series DC motor, and compound DC motor, which includes the stabilized compound. The series winding is not included in a shunt DC motor. It is included in a series DC motor, a compound DC motor, and even a stabilized DC motor. Here's a picture of a shunt pole winding with the series field wound around it without the iron core. Another picture of series wind field windings wound around each field pole, and notice the difference in the wire size between the shunt pole winding and the series field winding. That has everything to do with the amount of armature current that flows in the motor in this series winding. Here's an illustration of how a series winding is wired out to the wiring box. Leads are labeled S1 and S2. You must be very respectful how we connect these leads so that the flux generated by the series field aids the flux field in a cumulative motor. As armature current increases, so does the series field flux contribution, as shown here. Brush rigging is an essential component in a DC motor that ensures proper contact between the brushes and the commutator, allowing for efficient transfer of electrical energy. It's made up of different parts: brushes, springs, holders, arms, insulators, and a yoke. Brushes are typically made of carbon or electrographite materials, and they're designed to make physical contact with the commutator. By maintaining constant contact, brushes facilitate the flow of electric current. Brush holders are responsible for holding the carbon brushes in place and maintaining their position. And by holding the brushes, the brush holders ensure consistent contact with the commutator, minimizing potential arcing or sparking. Additionally, they also allow convenient replacement of the brushes when they wear out. Brush springs play a critical role in maintaining the appropriate pressure between brushes and the commutator. These springs are usually made of phosphor, bronze, or stainless steel, as materials like that possess flexibility and resilience. The springs exert a controlled force on the brushes, ensuring a sufficient contact pressure without causing excessive wear or damage to the com. Here's a video exploring the components of the brush rigging. The brush arm insulators must be cleaned during PM opportunities. The brush arms are zinc plated to prevent corrosion. We do not accept these type connectors where you have two leads going into one connector. We prefer a single connector for each lead and a six-sided crimp lug. There's the brush arms, the brush arm insulators, brush holders, springs, shunts, brushes. And this is a 4-pole motor with 4 brush arms.